the right box. Okay, so hmm. Mhm. Okay, so let's get started. This previously, Arath and I discussed about doing a presentation on uh, what? Give me a minute. Give me a minute. Um, Yeah, so discussed about doing a presentation on proximal policy optimization, which is like a popular uh, policy optimization algorithm from OpenAI, which was published in 2017 and which is widely used uh, in places where people do reinforcement learning. When I was uh, so So this is the proximal policy optimization algorithm. And then if you look at this paper, it starts with a policy gradient method. So policy gradient is one of the ways in which reinforcement learning can be done. And it starts with it starts with an empirical policy gradient estimator. So if you let's say I will give some uh, uh, intuition. Like I will start with some like let's say uh, you have some function of some value x, and usually we are familiar with loss functions, right? So in loss functions our goal is to see minimize the loss. So we do some gradient descent and we try to find this global minimum kind of spot. That is one gradient method that we are very familiar with. So if let's say if something is or some f of x is desirable, this is loss is undesirable, right? So we want to minimize that. So if some uh, function of x is which is desirable, then we need to maximize it. Like we need to find the highest. So these are like you can just put a negative of it and then do gradient descent, or just keep it as it is, do gradient ascent. So let's say if this function is a policy, some sort of policy, let's say some sort of policy to earn money. So you want to maximize that. So once you are at that point, whatever you do will maximize the amount of money that you want. So that is kind of like an intuition of policy gradient. Uh, why do we do this kind of gradient ways in policy optimization? So these are the table of contents, introduction to rain. So not everyone in the audience is taken RL course as like Arthman said in the group. So I added a few slides to give an introduction on reinforcement learning. Then MDP framework, Markov decision process. That's like that's like the bedrock of this RL formalization from which they build all these methods. Then we I will just show the policy gradient estimator. Then the rest of the presentation is about how we get the policy gradient estimator. So this is just some probability kind of derivation to arrive at the policy gradient estimator, which is the starting point in this uh, PPO paper. So I thought it will like these are just like some basic steps where you do this kind of expectation and then do gradient methods to get this policy gradient estimation. So I thought it's a good exercise to like rigorously see how we get this equation. So the PPO paper is about you take this policy gradient estimator, then uh, like you optimize like you do a proximal optimization. You define let's say you have a complex function that is difficult to optimize. Then what you do is you find some sort of function that is correlated with that function, then you optimize that function. Those are kind of techniques in optimization. So PPO is kind of like not exactly that, but kind of like that for optimizing policy gradient. So like I thought it will be interesting to understand what actual the policy gradient is before we go on to do, okay, we can optimize, we can change, like slightly change it like this and then optimize it. So that's my plan. So the rest is like, if you are familiar with probability and these gradients and stuff, it should be a breeze. Like there are a lot of slides because like I prepared this with Gemini, and like it is very verbose, and I didn't have the patience to edit all the verbosity out of it. Yeah, that's the plan. So any questions until this point?
Nope.
Okay, I will move on. So okay, so reinforcement learning is slightly different from the other types of learning that we do, like supervised, unsupervised learnings, in one key area. So in standard machine learning, the data set is usually fixed. So in supervised learning, unsupervised learning, let's say you do some kind of the ImageNet, you take the ImageNet data set and then you do some learning on it. Then the data set remains static, and then you learn some models which is trying to extract some information or something from the data set, and the data distribution doesn't change. Let's say there are 10 pictures of a dog, and you are going to like, if you randomly sample from it, you are going to 1 out of 10 times you are going to see that each dog, right? So that is the distribution over the data that we have in the other learning scenarios. But in reinforcement learning, there's a fundamental difference where there is no fixed data set. Okay, the agent or the algorithm uh, interacts with the environment, and then you get certain rewards and state transitions based on the interactions that the agent makes with the environment. And the key point to note is that the actions the network takes dictate the data it will see in the future. So here, in other learnings, like if you optimize the network parameters, neural network parameters, theta, it doesn't change this distribution over the 10 dogs. Like you are still going to see the 10 dogs again and again. But in reinforcement learning, once you update this network parameter theta, the data that you are going to see in the future is going to change. The agent is going to take different paths, different actions, and then the environment is going to show you different states based on your changed preferences. So the data distribution is non-stationary and explicitly depends on the model itself. So this introduces some mathematical constraints when we are doing the similar gradient optimization methods that we do for other learnings. But there are ways around it. Like there are simple mathematical reformulations where you can still reformulate it in slightly different ways, or you can still do gradient learning with backpropagation and whatnot. So yeah, that's the slight difference between two areas. So any questions on that?
Nope.
Okay, so the other, so the RL is like a wide area, but I will just take the one route that will lead us to policy gradient. So there are a lot of other branches, but we will take one route. Yeah, so the formalization of this agent environment interaction is the Markov decision process. So in that, like you have a set of states, capital S, and then the agent can choose a set of actions, capital A, based on that state. So function of A given S. So agent will choose an action given the state that it is in. Then once the agent is at particular state, and once the agent takes a particular uh, action A, then this action affects the environment or the state of the environment that the agent experiences. Then the let's say this happens at time t, then at t plus 1, the state changes to st plus 1. Let's say this state is st. Then let's say you have light bulb and a switch, and the light bulb is off, then the state 1 can be off, and your agent flips the switch, then the next state will be on. So if you consider this light bulb switch system as the environment, and your agents flipping as the action space, then once you flip it, it changes, the environment changes. So that's the kind of idea here. And then every time this happens, like we take an action and the environment changes states, you get a reward. In the simple example we took, the light we get, let's say we are studying in the night, then if you flip the switch, you get light. So having good light is a positive reward. There can be negative rewards as well, like for taking bad action. So this framework captures this. Any confusions in this?
No.
Okay, so yeah, so then there is a notion of trajectory. So if you do this again and again, let's say you are initially at a state S naught, you take action A naught, and then you get a reward R naught by doing A naught at S naught. Then at the next step, your environment changes from S naught to S1. Then in the new state, you take another action, you get another reward, and then you keep on doing it until T is equal to 1 to T is equal to T. Then all these collection of state, action, and reward data is called a trajectory. This is just some collection of the history. Then these are like fun diagrams, like people show to explain agent environment interaction. So if you take an AI robo which is navigating some maze, then the robo can take some action like turn left and right, move forward, and you get a state and a reward. You get a new location in the maze, and also if it is an exit, then you get a positive reward. If there's a hole or something, then you get a negative reward, something like so. This is some way of thinking of this kind of framework. And then usually the agent will have some learning algorithm, and like these are interconnected things. Like you have a policy, and then you have an optimization on that policy. So the you will be in a state, the agent will know the state and then take an action. Then based on the reward, you learn a policy where you try to maximize the rewards over time. So we will get to that. Okay, so so we have the framework of agent environment interaction in a formal setting, and the goal of the agent is to maximize the expected return. So you do this trajectory and get R naught, R1 up to RT, right? So let's say if you take a summation of RT, T is equal to 1 to capital T, the goal of the agent is to get as maximum total cumulative reward as possible. That is what they are saying here. And there are several ways of doing RL, and in deep neural network based RLs, we define a neural network with weights theta as the policy. So you have a neural network, and into the neural network, you put the state T, and it will prediction action T based on that state. Then this neural network is called the policy, because like our policy, what is our policy? The policy is taking an action based on the state. So if the neural network parameters are theta, then that's what they're saying here. This is policy, and the notation they use is pi theta at given st. So st is given, and given this, you take an action at, and they formalize this neural network as a function pi, and the function depends on the. So neural networks are special kind of functions, right? Like you can change the parameters, and then not special kind. Like every function has parameterization. So that parameterization is denoted by theta, and every time you change the theta, the behavior of the neural network changes. So that's what they're showing here. The agent's sole objective is to find weights theta that maximize the cumulative sum of rewards over trajectory. So that's what we saw. So we want to like adjust theta in such a way that the total expected reward. So that's what they are showing here. If j theta is the RL objective function, and this is the summation we saw before, RT is the reward at time t, then you sum the rewards from 0 to capital T, and then this is not a static thing. So it changes based on the trajectories you experience based on your policy. So you want to maximize the expected sum of cumulative. Uh, so the expectation of cumulative sum of rewards. So there is a distribution of like there's a the reward cumulative reward is a distribution. You want to maximize the expected value of that. Where the trajectory is distributed over pi theta. So this is what we meant when we said the the actions network take dictates the data it will see in the future. So if you consider trajectory as the data, then our the trajectory is kind of distributed over pi. We will see how the policy and trajectory are connected. There's a specific formula how it is connected. So in usual learnings, like expectation is over some x comma y distributed over the data set, right? Like you have a data and a label, and then that is distributed over data set D. But here the trajectory is distributed over it's connected to a policy as well. We will see how in detail later. So any questions until this?
I have a question.
Yeah.
So is this loss differentiable?
Yes. So this is differentiable. So thank you for asking the question. So this, I think this entire presentation is about how we can differentiate this loss when this neural network parameters dictate the expectation. Because here you have some neural network parameterized by theta, then if you take a gradient, like this is, let's say this is your objective function, and then you take the gradient of the objective function, then you can differentiate the neural network and then do optimization. So here the parameters are controlling the expectation. So in that scenario, how we are going to differentiate this? So that is, I think that is the entire theme of this presentation. So we will see that in detail later, excruciating detail later. Yes.
Okay.
Any other question? Okay, I will move on. So I want to give you a broader landscape of RL, because if I just continue the presentation from here, people are going to think there's only policy grade, we can see there's a policy and then do gradient update on the policy, and then this is the only way of doing RL. No, there are other ways. There are three major paradigms, like value-based methods. So what they do is, let's say there are let's say this is like a state machine. There are like 4 states: S1, S2, S3, S4, and then this is your environment, and then agent can be here, and based on the actions, like your agent's state can change from this to this, and then each state, like in this framework, like each state will have a value v1, v2, v3, v4, and each state will have a value. Then this value-based methods will try to learn this value v or q. So v is just a function of state, and q is a function of state comma action. So in this state, taking one action can have a different value compared to taking a different action. Let's say you are in a car, and pressing the having a car or not having a car. Having a car is valuable, but having a car and then doing whatever you want to do with the car has different values. So that's what is. These are very popular, like Q learning, deep Q networks. So these are popular methods. Those are value based. So they depend on the value of being in a state, or value of being in a state and taking an action. So this is one way of doing RL. We are not going to talk about that. And then there are model based methods. So in these methods, what they do is they try to learn the environment transition dynamics. So in this, let's say an agent is here and you take an action, then it might go here or it might go here. So we have seen a notation for that before, I believe. So this is the transition dynamics. So if you are given ST, if you take AT, what is the probability of ending up in ST plus 1? So there are methods that try to learn this state transition dynamics, and then use that to extract a set of good actions to take. So these model-based methods are also there. So alpha 0, dreamer, mu 0, these are like some popular examples in model-based methods. Then the third one is policy-based methods. So this is what we have seen so far before as well. So parameterize and learn the policy directly as a probability distribution pi theta of A given S. Then you have this policy. This policies itself is like previously we have seen a neural network given a state will predict an action, right? So it doesn't need to be a deterministic neural network. Like we can have a distribution over set of A1, A2, A3. Then every time we give a state, the neural network can say, okay, this is the distribution 0.1, 0.5, 0.4. It can give a distribution over the set of optimal action. So we can sample from this distribution. A greedy way would be doing this highest probability output, or like you can do some exploration and do other. So this is the difference between exploration and exploitation when they when they talk about in RL, whether you do the maximum after learning a policy, if you always do the maximum value action, it is called exploitation. You have learned something, then you exploit that knowledge. If you are okay with trying out other low value actions as well, then that is called exploration. So that's like there are a lot of things in RL. We will just systematically slice and learn about the things that we need for PPO. Yeah, so there are reinforced vanilla policy gradient, PPO, GRPO. This was introduced by DeepSeek. I think this was from OpenAI. So these are all policy gradient, policy-based methods. And so these are the three major paradigms. And PPO is in a special class called actor critic method. So in PPO, we will see later. We not only we learn this pi theta, learning pi theta is policy method, but PPO also learns this value function Vs to reduce some variance. Like we will see that later in this presentation. So this PPO learns both pi theta and V theta. So these kind of algorithms are called actor critic methods, because actor is whatever is taking the action network. There will be a neural network that is predicting the action, and there will also be a neural network that is predicting the value of being in a state. So that is called the critic. So that is why they are calling this as actor critic method. So that is that's the subcategory of this PPO. But broadly speaking, it's a policy method. And these are major paradigms. There are a lot of other things, imitation learning and whatnot. Like my knowledge is not complete in this. So yeah, there are a lot of things. So this is like the broader landscape. Any questions on that before we dive into policy?
Yeah. What I understood, like PPO is like basically learning the distribution, and the first two was like methods were based on learning the value. Saying the model-based connection, if I'm not wrong.
Yes. So in reinforcement learning, you have there are different concepts, right? Like there are states, and then each state can have a value. Let's say you have a like a maze, and this is your goal. And if you reach here, you will get a high reward. You will get a prize. Let's say this is a hole. If you reach here, you will fall into it. Okay. Then the value of being in this state is higher than the value of being in this state, right? Because if you're just one step away from getting a high reward, but the value of here, you're just one step away from just falling into a hole. So the states can have intrinsic value. So the value-based methods will try to learn that distribution, like over the states, what is the value of being in the state. Then that is not enough actually. So they do this Q learning, where Q learning is a function of both state and action. So the value of, let's say here is a hole again, then the value of being in this state is like not very determined, right? Like, but if you're here and you go up, it has higher value. If you're here and if you go down, it has very low value because you fall into a hole, right? So That is what. So this Q learning is like it is useful to learn. If you are in a state and you take an action, what is the value of doing that? So yeah, that is value-based methods. Then model-based methods, they try to learn the transition dynamics of the environment. So here you are just trying to learn, okay, you are in this state, you are taking this action, but it's the reward we get. But the other picture is like you are here, you take an action, and then you end up in a different state. If you're A1, S1, and then transition to S2. So there are methods that try to predict this transition dynamics. So let's not worry about them because they are out of scope for this presentation. So the one that we are focused in is in policy-based methods. So yeah, so that's where we are going to go deep into. I hope I have
Okay, go ahead.
yeah. So yes, any other questions? Makes okay, I'll proceed. So the policy, a differentiable function. So from roles to policy. So there are different ways of doing policy learning or like policy-based methods in RL. The very trivial way of doing it would be to do a hard-coded rule. So every time you are in a state, you have some knowledge about some domain knowledge. So you say, okay, if you are in this state, take this action. So there can be like a lookup table kind of situation with policy. Or we can have the policy as a stochastic function. So if you are in a state S, there's not just one action, there are distribution. There are, if this is the action space, there is a distribution. So this is a continuous representation, but it's discrete. So if you are in some state, doing some action has high value, but there are other actions of comparable value, and there are like very bad actions in that state that you can. So this kind of distribution we can try to learn. So this pi of a given s need not be just one value; it can be a probability distribution. That's what they are saying here. So if you are in state S and currently your parameters are theta, so what is the probability of taking action A? So this is the formulation that we will use moving forward. So any questions on that?
Nope.
Okay, so as I have mentioned, we can parameterize this policy by a neural network, and the neural network can output some logics, and then we can do a softmax to like bring it to a normalization. Then you can consider the outputs as probability distribution over the set of actions. Then neural networks are differentiable. So then we can just calculate the so the question that Moj raised still remains how we can actually do this gradient, because that depends on the expectation over this, so that we will dig deep into it. For the moment, let's assume that the objective function we have is differentiable. Then what we can do is we can just do gradient. We can differentiate the objective function, take an alpha step in the positive direction, then update the network parameters step by step. This is like a broad idea of gradient ascent. So this here we will do gradient ascent, not gradient descent, because we want to maximize the value we get out of the policy. You can always do minus pi theta a given S and then do gradient descent. It's equivalent. Let's stick to gradient descent for this presentation, because that's what that's the what do you call that? That's the custom in this area. So if it is differentiable, then we take gradient steps, and then hopefully you reach a maximum value in the neural network parameters that can give you the highest objective function. So that's like the formulation. Then we move on to why is the gradient hard? Why is the gradient that we have to take over the objective function is hard in this? So we remember that j theta is expectation over the reward. This capital R is just a summation over like RT is equal to 0 to capital T. You can just denote that summation by capital R. Then you want to take the gradient of the expectation over the cumulative rewards. Why is it hard? It is hard because the environment is unknown, and we don't know the like this tau. The trajectory is distributed over our policy network, and we don't know this distribution. We don't know how given a theta, what is the probability of experiencing a trajectory. We don't know this. This depends on the environment, and this probability of experiencing tau given theta is a chain of probabilities consisting of both our policy. We will see that formulation below, and the environment's transition dynamics. And in this transition, like in policy-based methods, like we consider this as like a black box. We don't try to learn this. We try to only work on our policy space, and but our expectation is over this tau, and without knowing this tau is again a function of both our policy and the transition dynamics, and this we have control over. This is our neural network. With this, it is a black box, and we cannot differentiate over a black box. So our gradients cannot pass through a black box. Then we need some kind of a mathematical workarounds, so we can just work on the policy space and not worry about learning the environment dynamics. So we will see that in step by step. Like it's like some I don't know, basic math way of doing that. So I think, yeah. So any questions up to this? Okay, I will move on.
What is
Yeah, sorry, go ahead.
Yeah, what is alpha in the slide then?
Sorry,
What is the alpha before this slide? Yeah.
this one. Yeah, this is a hyperparameter. Like in gradient descent, also we have this step size, right? Like if you have a gradient value, then you want, like, if you're, let's say this is like, oops, if this is your gradient function and this is the minimum, and you are here, you know the direction to go, but whether you want to go this much or this much, that is controlled by alpha. This is like a step size. That's like yeah, that's from that's a hyperparameter basically.
Okay.
So policy gradient. So the gradient of the policy, like since policy, we don't know the exact function of the policy, we can only estimate it. Like we cannot like analytically find the like the derivative of the policy network, right? So we can only no, we can actually do the backpropagation differentiation, but we need to do some kind of empirical average over the set of observations that we make. If we take an agent and then let it run and gather some trajectories, then we can only estimate. So it's like stochastic gradient descent, right? Like you at each point you don't go through the entire data set. You just take a sample of the batch and then you make an empirical update, some estimate. So that SGD step will be some estimation of the actual gradient. So similar concept applies here as well. So the policy gradient estimator. So policy gradient methods compute an estimator of the policy gradient and plug it into stochastic gradient descent algorithm. The fundamental gradient estimator is this. This is the equation that is shown in the paper. The policy gradient expectation estimator is expectation over t, gradient of log of our policy pi theta multiplied by a function called advantage. Let's not worry about a here. Let's just think it is RT, like some sum of simple RT. So there's a slight difference between capital RT and AT, which I will get to I think in the last slide. So the policy gradient estimator is basically the gradient of log of our policy function multiplied by the cumulative sum of rewards. So just tell me what you understand from this. Like what is this telling you? Any ideas? Anyone? Any ideas?
What do you mean?
Like what do you think about this? Like what happens when you plug in some values for policy and some reward? What do you think happens to the gradient estimator? Like it's open-ended question. Any thoughts on this in this formula? Yeah, so that's like an open-ended question. I just wanted to see if anyone had any thoughts. Does it look good? Does it look wrong? Or can someone do better than this? So that's the kind of thing. So let's say the cumulative sum of rewards can be positive or negative. If you do some sort of BS actions a lot of times, if your policy is really bad, the total reward you get can be negative. Then the log function, I think I forgot how the log function looks like. So I think it's like it monotonically increases with yeah, let me just yeah, so the log function, if it is x, if it is log x, the function is, I think, something like this. It crosses at 1. So if x increases, log x also increases. There's no way we think, so it's fine. So if we get some high policy, then the log of that high policy signal will also be positive. So that's fine. So if there is a positive reward, then we want to maximize that chances of taking the actions that is leading to positive reward. So we multiply this by a positive number. Then the gradient moves let's say this is our distribution of the pi theta. Then there are some actions that increases the reward. Then you want to take you want to go towards the direction that maximizes the likelihood of those actions. Then there are some actions that gives you a lot of negative rewards. Then you want to move the network away from those points. Like if you reach here, you will get the very, very negative rewards. So you want to move away. So that can be elegantly just handled by multiplying this value by whatever the reward or the advantage that we get. So we are going to dive deep into this. I just want to give you some taste of what it is. So yeah. So anyone now any thoughts on why this is a good policy estimator, like estimator of policy gradient? Or like I'll just move on to how you derive this from the fundamental definition of the value function we had, the J. Okay, I'll move on. So if there are any mistakes, just point out to me. So I vibe created most I think 70% I just vibe created. So maybe mistakes. So yeah. So we'll start with some refresher. So what is an expectation? Let's say you have value function fx, and then for every x you have some value. Then each x also has let's say there are just two, x1 and x2. x1 has a high value, x2 has a low value, but x2 has like a probability of x2 is like 0.9. Probability of x1 happening is 0.1. Then you have to weight that, right? Like when you are trying to get the average of the value that you get. So the average value will be not fx1 plus fx2 by 2. It will be, you have to weight by these values, right? Like it will be fx1 times 0.1 fx 0.9. This will be the average, like expected average. So that's the kind of thing that is shown here. So the expected value of fx when x is distributed in a probability distribution P is this sum of, if x is discrete, the sum of probability of x multiplied by f of x. Agree or disagree? Anyone disagrees with this?
No, it's good.
Okay, yeah, this is basic expectation. So when you're taking an expectation of a function, when the function variable is distributed over some probability distribution P, then you can sum the f of x multiplied by the probability mass of that particular x. Then you take a sum over all the x's that are in the domain. So that's okay. So let's go back to how we take the objective of a supervised learning setting. So let's say you have some x data, you have labels y, and then you have a neural network f theta. You can plug the data into neural network and you get the prediction f of f theta of x. This is like the prediction from the neural. Then you can compare this prediction with the actual label and then calculate some loss, right? You can do that for every data. So that is what is shown here. So a loss, we have to minimize that because this prediction has to match the actual label. Then this loss can be considered a function, and then you weigh it by the probability of this x and y pairs, this data and label pair. You weigh it by the probability of seeing that xy pair in the data set, and then you just calculate the sum over all the losses over all the x and y's in the data set. Usually this is like, you can just, what you can do is you can just take a sum over all the thing and divide by the size of the data set, because usually if there are n x y pairs in a data set, the probability of like we are just doing random sampling, so the probability of seeing that will be 1 by n, unless we do some kind of shifted sampling or something, basically. So but if you expand it out, this is like this. So summation over xy, probability of xy, loss of that specific example. Agree?
Yeah.
Okay. So then what we want to do, we want to minimize this loss. Here it is an undesirable thing, loss. So we want to minimize this. How do you minimize? You take the gradient, then you take a step in the direction that minimizes that function. So you take the gradient of that function, which is gradient of this entire sum. Then we can see that like this, if you consider this and this summation, like the like this gradient and gradient is like let's say there are two function f1 and f2, and then is equal to g, then both of them are dependent on x. My calculus may be wrong, correct me if I'm wrong. So if you take dg of x over d of x, that is equal to d of f1 plus f2 over d of x, that is equal to d of f1 over x, d of x plus I'll continue d of f2 over d of x. You can just distribute the differentiation over summation, right? Agree?
Yeah.
Okay. So this is similar. So this is just one dimensional. If there are x1, x2 and multiple dimension, then it becomes this nabla notation. Then you can just distribute this nabla over this sum, and this also doesn't depend on your network weights theta. Then the gradient operator just affects the loss. So you take the gradient of the loss. So in order to calculate the gradient of the value function, like the objective function, what you can do is you can take the gradient of the log, like after distributing, you can take the gradient of the loss function and then multiply it by the probability of seeing that XY pair that led to this specific gradient, then sum over all the gradients that you see, and then that will be your gradient of the objective function. So but ideally we want to maximize or minimize an objective. Then loss is like a proxy to that objective. Then since this is like distributed, you can just take the gradient of the loss and then minimize or maximize it to achieve the objective on your objective function. So this is like, these are basic, so we don't worry about these things, but this is formally, this is what happens. So okay, so we have seen that this is sum over the probability distribution P of X comma Y. So we have seen that this if you have a sum of some function of weighted by a probability distribution P, then it is an expectation of that function where X is distributed by that function P. And in order to approximate this, what you can do is you can sample X from P. Let's say if your P of X is like this, you can just sample a few times from this probability distribution, plug it into F of X, then you calculate the average of all that. Then this is then you can consider that is the expected value, right? That's what we usually do. If there is an expectation, then we can just sample X from the distribution, then calculate the value of that X, then just average it to get the expected value. So that is what we usually do when we are training models. We just sample X and Y from the data set, then calculate the loss for that particular data label pair, and then you do it like maybe, I don't know, maybe a few 100,000 million times. Then you say that it's like the gradient of the objective function. So here it becomes an expectation because we have summation over a probability distribution P of X comma Y, and then you have some sort of function here. So it becomes an expectation over that distribution. Here the distribution is the data set, and then you have the function. Any questions here?
Nope.
Okay, so the way to empirically do this is like just sample X and Y from the data set and then calculate the loss, and then do it until you are satisfied. Okay, so that is about the other learning scenarios where the data set is static. But we have seen that the reinforcement learning data set is not static. So this is the objective function that we have seen before, right? Like, do you remember, like we have seen it in, yeah. Okay, I missed it. So where is that? It should be before this. Okay, let's not worry about that. Let's you guys remember this this equation, right? Like our objective function here is the reward that you get in a trajectory and the probability of experiencing that trajectory given our parameters theta. Then you need to take a sum over all the trajectories. This is the you can intuitively think of it. So let's say there are different, like let's say you start from here, this is your starting, then there are several ways that your problem can go. Then this one has some R1, this one has some, so at each point in the trajectory you get R1, R2, then you take a sum over it and then it becomes a capital R. Then you have different capital R, capital R2, R2, R3, R4. Then for each of these trajectories, there is a probability. Okay. And then if you want to find the expectation of the cumulative reward capital R, then you want to multiply that with the probability of experience. First, you need to know what is the probability of experiencing that particular trajectory. And then you want the value of that trajectory R. Then you just multiply it, take a sum over it. Agree? Okay. So, but the difficulty comes here is that the neural network parameter theta affects the probability distribution over this trajectory. Let's say you have some sort of parameters theta 1 to your network, then 0.5% of the time we are going to experience this trajectory 0.1, 0.1, 0.1, 0.1. This is the weight over this trajectory. But once you update the theta 1 to theta 2, then this distribution itself changes. So the probability of experiencing some trajectory changes. The data, this is why they say the data distribution changes once you update the neural network parameters. So yeah, so this is some intuition behind that. So this probability of tau given theta is dependent on your neural network parameters theta. Okay. So once you, this is your objective function. If you want to, here we want to do the maximization. So if you want to take the gradient of the nabla of j theta, gradient of the objective function, then again, here is you have a summation. You can just bring the nabla into the sum. You can distribute the different derivative over the summation. You can bring the nabla inside. But here, the nabla is applying to this probability distribution. Previously, the probability distribution, probability of x comma y, loss of f theta, right? So previously when we did that, the gradient came here to the loss function. Now this reward, it is not, it is a function of your environment. Like the environment, like if you go back to the simple, where's the yeah, so a simple environment resource. So here you have a good reward, like if you reach the goal, if you reach these halls, like you get a bad reward. This itself doesn't change when you update theta. Like when you change theta, this reward is not going to move here. It is still going to, if you change theta, it is, this hall is not going to move here. It's still going to stay here. So the reward is determined by the environment, which is not affected by your updates in the policy network. However, what is affected is the probability of experiencing certain trajectories. So that's what is shown here. So this is not a formula for expectation. So for expectation, we need to have something like this: summation over some probability distribution into some function. This function can be some f of x or gradient of f of x, so it can be something. Then if it is of this form, summation over probability distribution and then some function of that variable, then you can do, this is like an expectation. Then you can do empirical sampling. You can sample some x from that distribution P, then calculate this something, then average it to get the actual value of this. But here, this is not, we have something like this, summation of a gradient of probability distribution multiplied by something. So here, since the gradient is applying to the probability distribution, we cannot simply do, okay, you sample x from that probability distribution, then you calculate the something, then you calculate this gradient somehow, and then do empirical averaging. So this is the fundamental limitation that we talked about before. So in a more formal way. So any questions on this? Okay, I will move on. So the math is pretty simple. So what you can so consider, let's say you have so here, now we are going to try to switch this formulation into this formulation where we have a summation over some probability distribution. So okay, now let's start with clean slate, where if y is equal to log of x, what is dy over d of x? It is 1 over x, right? Correct me if I'm wrong. Okay, so so let's say if you have y is equal to log of f of x, then dy over d of x is equal to 1 over f of x into df of x over d of x, right? Agree?
Yes.
My calculus is 10-year-old, so I can make mistakes. So correct me if I'm wrong. So So now consider the gradient of log of probability of experiencing the tau given theta. So here we have probability of tau given theta. Let's just consider this. Let's consider gradient of log of probability of theta. That is like this. So 1 over that, and then the gradient of that. Okay. So if you take this p as this f of x here, you get 1 over p, then gradient of that p. So you have this 1 over p here, then gradient of that p here. Agree?
Yeah.
Okay, then you bring this here. You can just rearrange this and create this log derivative identity where gradient of some probability p is equal to p into gradient of log of that function. This is like a log derivative identity. It's just a simple result. So we are going to use this result to try to do some gymnastics to enable this empirical sampling based learning. Then I think it's well. At what time do you expect me to stop, Bharat?
No, you can keep going.
Okay, so the rest of the slides are just this step-by-step derivation, so it should be fast. So okay, so now what we do is you just plug this into this. You replace this by this identity, this part. Okay, so that is what is shown here. Now gradient of j theta is equal to summation over not just previously here was grade of p tau given theta, right? We have replaced that with this identity that we saw before. Now, if you just break it here, if you consider this is a probability distribution, now we have a sum over some probability distribution times some stuff, right? Agree? Then we can think of this as an expectation. Like we have still not solved our problems completely, but we can think of this as an expectation of over this. Okay, so now we can think of this as an expectation of tau distributed over our policy of this function, gradient of log p tau given theta and RT. Agree? A simple substitution. So I will move on. Now we had to do further stuff, like we had to this equation is far from the gradient estimator that we have, right? Yeah, gradient. We have to somehow get here. So we have some steps, non-trivial steps before we reach there. So we'll see. So we will see how the trajectory is distributed over. Okay. So let's say you are in a state S naught, and then you take an action A naught, then you go to S1. Then from the S naught, you take another action A1, then you go to S2. So this is one trajectory, right? Okay. You are in S naught, then you take some specific action A naught, then you reach the state S1, then you take another action A1, some specific action, then you reach S2. This can be one trajectory. And what is the probability of this trajectory? The probability of this trajectory is, first we have to start with this. What is the probability of this initial state S naught? Then what is the probability of taking the action A naught at S naught? This is our policy. Okay. What is the probability of taking action A naught at S naught? And then by doing this, the environment transition from S naught to S1. So you have to multiply that by the probability of S1 given S naught comma A naught. Agree? If you want to come until this point, you have to start. It's like chain rule of probability, right? Like you see the probability of this, then given this, what is the probability of taking the action? And given these two, what is the probability of this S1? Okay. Then since this continues, we have to see what is the probability of taking A1 given S1. So now after coming here, we are in S1. What is the probability of taking the action as A1 given S1? Then we have to multiply that by probability of S2 given A1 comma S1. Agree? Because the state transition from S1 to S2. Agree? So this long multiplication is the probability of this trajectory. Agree?
Yeah.
So that is what is shown here. So here I have shown S0 to S2. Here they have gone from S0 until S capital T. So for probability of some specific trajectory T given theta is probability of S0 starting at S0 times. So these are our pi. So probability of taking some action at some state is pi. Okay, so that is what is here. So initially if it is 0, we start with 0 probability of S0. Then at S0, what is the probability of taking action A0? Then by taking that action, what is the probability of state transition to the next state? Then it keeps on chaining like this. This is like the multiplication. So this keeps on chaining until the end. So this is the probability of experiencing some trajectory tau given theta. Agree?
Yeah.
Okay, so here, this is within our control. This is our neural network. But this is a black box to us. We don't know how the state transitions from one to another by our actions. There are other like model-based approaches that try to explicitly learn this, but currently we are focused on just focusing on this part. Like we want to just not consider about the environment dynamics. So again, log. So you take, this is a multiplication. Then what we do is we take the logarithm both sides. So you log of the probability of experiencing tau given theta is, you just change all the multiplications to additions now. So initially we had this probability of S0, it becomes log probability of S0, and this entire multiplications become a big summation, and inside that we have another multiplication, then it is again becoming an addition because of again taking logarithm. This is just log. Questions?
No.
Okay, now you take the derivative. You take this equation, take the gradient with respect to your neural network parameters theta. You take the gradient of this entire thing. You can see that only this part is depending on theta. This doesn't have any theta. This doesn't have any theta. So these both go to 0, right? Got it?
Yeah.
Yeah. So now the gradient of log of the probability of trajectory given theta is just this part. Sum of t is equal to 0 to capital T. Gradient of log of pi theta of action given state. Now we have completely removed the environment. So the environment. So we had a dependency on our trajectory, and the trajectory depends on both our action, like our policy, and also the state transition dynamics. And just doing this kind of log, taking log, we have removed the environment dependency, probability of environment dynamics. This is the environment dynamics from our equation. Then here, so this is, so previously we had this, right? We did another, we did a log trick to like make this equation into an expectation, and we had this this part, right? Now we are going to here it is the probability of experiencing tau given theta. Now we have elegantly like removed the dependency on the state dynamics from this this part. So we are going to we have found a way to remove the state dependency the environment dependency, and we are going to plug it back inside the previous formulation that we had. Gradient of j theta is the expectation RT times. Previously here we had I think gradient of probability of tau given theta. Correct me if I'm wrong. So we have found a way to replace that with this summation, which removed the dependency on the state dynamics. So this is why. So now the direction of change in the objective to maximize or minimize it is just a function of our neural network and the rewards that we see from the environment. So probability of st plus 1 given st comma at, this is the transition dynamics. This is the black box part that we had. We removed it. So now, since we have this, model free learning is mathematically very sound. Like we can just do empirical science. Let's say, okay, we have a policy network, we have an agent, we just let it play, we collect some rewards, and then you just update the policy networks to maximize the rewards. And like we can just do empirical science like this, but RL has these theoretical groundings which show that just ignoring the environment and focusing on our policy, and then you should have the right forms, like you should have the log and all these right things, then model free learning we can do. So that is what is shown here. Any questions on this?
No.
Okay. So again, the rest is some math, some gymnastics. So this is the equation that we have here. Then you the expectation of operator is linear, so you can expectation of sum of something is the sum of expectation of that something. So you just put the expectation inside. So we are going to do some additional steps to bring it to that gradient estimator equation that we had before. So you just distribute that expectation operation, and then okay, now we are okay. Now we have another part. Like here, see this reward R tau. This is the cumulative sum of rewards. Like you take the sum of all the rewards. So let's say let's consider this timeline. So t started from 0, 1, 2, 3, and then you come to t dash, and then you go to until capital T. This is your window of doing this optimization. Then let's say at this point you want to decide what action to take. Like that is captured by this part, but you are multiplying that by the entire reward that you get from this trajectory. Okay, then when you are deciding on some action here, you have already taken some actions in this part, and you have already collected some rewards R dash, and then the rest of the rewards are going to be R double dash, and this R tau is going to be R dash plus R double dash, right? Agree? Yeah. So at this point T dash, you are taking some action, and that action is going to affect the rewards you see after this. Before this, like you have already experienced that, and after experiencing that, you are taking some action, and then that action is only going to affect the future. It cannot go retroactively and affect the previous rewards that you saw. But here in our formulation, we still have this entire cumulative sum. So we are going to see how we can just throw it. This is called disregarding the past, like just getting rid of the past. We can just say, okay, let's just throw away R dash, and then just put R, I don't know, R is equal to R double dash is equal to sum of T is equal to T to T, not from 0 to T, but from T to T. You can do it, but let's see how we do that, how we can actually remove that. We are going to end up doing it, but let's see how rigorously we are going to arrive at that point. Okay, so this is called some credit assignment problem, how we are going to assign the credit to each action you took along the way from the cumulative reward. So this R tau, you can split it into this. If you are currently at a time step T dash, then this is the past reward and this is the future reward. Got it? We have seen that before. Okay. Then in this, you can just break this equation into two. by splitting the rewards. You have this part stays the same, but now you have two different summations. One is the past and one is the present. Okay. Then when you do an expectation over this, when you do an expectation like this is the something that we have, but we have an expectation here, right? We have an expectation over this part. So we are going to see why, like the expectation over this, the log of this and the future rewards, this is non-zero, but this part is zero. This part goes to zero. We are going to see why. So for that, like again, some simple math. So score function identity. So let's consider this. Okay, some expectation of gradient of log of p theta. If you let's consider this, and then we have the log derivative identity, right? Like that we okay, no. So this expectation, we can write the expectation as a sum, right? Expectation of x distributed over p theta times something is the sum of that probability mass times that something. We have seen this is the definition of expectation, right? So we are deconstructing this into the definition of the expectation, where expectation is written as a sum of x over p of x multiplied by this. Then we have seen the log derivative identity, right? If you take d of log of f of x is equal to d of f of x over f of x, right? So we are just rewriting this as this part. 1 over f of x is here, and then gradient of f of x is here. So gradient of log of something can be written as this. And then if you look at it here, since this expectation was also over the same probability function, these two are the same. You can just cancel them, right? Then this becomes summation over x gradient of p of x, right? And we know that like this sum of gradient of functions is a gradient of sum of functions, right? Like that gradient operation also is distributive. So previously we took the gradient inside. Now, so now we are going to take the gradient outside. So we have the gradient inside. You can just take it outside, and now see this part. This is just gradient of sum over some probability of probability function. Okay, so if this is all, like we know that like if there is a x and you know a p of x and there is a function, then integration of p of x d of x is always 1, like because that is the definition of probability functions, right? Like you need the area under the curve should be 1. Agree?
Yeah.
So this that is continuous space. In discrete space, this is the equivalent of this equation. Then the sum of the probability mass distribution is just 1. Then gradient of 1 is 0. Then what this says is this is just an identity, again an identity where the expectation of the gradient of some log of probability function is 0. That is what is shown here. We are going to use that to eliminate the past from here. So consider this expectation over the past, and since so there are like there is another law, that law of iterated expectations, where if you have an expectation over the over some space, you can just break it into expectation over past, and then like this I am not exactly clear on. Like, so what you can do is you can break this expectation into the expectation over past, and then you take an action at time t, and then you since this at doesn't affect this, so with respect to if you take expectation over at, and you have some f1 and f2, and then this f1 is affected by at, but f2 is not affected by at, then what you can do is you can do f2 times expectation over at times f1, right? Because with respect to that particular action, this is constant. So you can just take that constant out, and then just consider the expectation over the function that actually depends on that action. So you take an expectation over action at that time distributed over the probability distribution pi. Then you bring that this is a constant with respect to this at action at time t, because all this happens before t. This is a constant. Then this like just read about it. Like, I'm also not 100% clear. I just got this from the internet. So this expectation can be broken into these parts. Like you take the expectation of a past, and then you can just take an expectation over action, and then consider only the action, only the parts of the formula that depends on that action. So this is it is the law of iterated expectations. I kind of understand it, but I cannot I don't understand well enough to explain it. So just trust me when just question me. Maybe this may be wrong. Just read up about it. So this is how the derivation is shown. So so when you take this expectation over this log of this, and this is a probability distribution, and we take the expectation over that probability distribution, and then gradient of log of probability distribution, and the expectation over that distribution, we have seen the log derivative identity that it is 0, right? So this part goes to 0, and if it is 0, then this entire thing goes to 0. So this entire thing is what we had as the past component here. So this part is the past component of our policy gradient. This is the future component of our policy gradient, and we have used some basic identities to show that this past component goes to 0. So if even if I have not explained it properly, we can let's just assume that we are taking only the future rewards, not the past rewards. We are just disregarding in the past rewards, but there is a mathematical reason as to why we can actually do that in our formula. So in our so we go back to the gradient of our objective function j theta. So previously we had sum from 0 to t. Now, since we have eliminated the previous, like the past rewards, now we have this this formulation. This formulation. Now we have come out until this part. Okay. Any big misunderstanding? Any questions? I think we will have questions here because I am sure I didn't explain it pretty well. So any questions until this?
Yeah, we'll have to read about the previous part a little bit.
Yeah. I think sorry, like I didn't look at it well enough. So yeah. So just know that like we got until the part where we have log. We removed the environment dependency, and then we also removed the past reward component when we are taking action at time at. So we have this formulation now, and then they say like this, just the sum of rewards is like a very noisy signal. Like it has high variance, and this theory is separate from, I think, the advantage function. I'm not sure if it is introduced in PPO or not, but the basic idea is this. Let's say you have some states S1, S2, S3, S4, and then you jump from different states, and then you have let's say you are in this state S1, and then you take A1, and then you get a reward R1. Okay. Then you go to S2. Previously, what we are doing is we are just summing up R1, R2, R3, R4, all the rewards, right? What they are saying is this sum over all the rewards can have high variance. I don't know why it is true, but this is let's just take it as a ground truth. This is a high variance signal. What you can do, like we have seen that like some states have a value, some intrinsic value, right? Like if this state is close to some reward, some high reward, then this state intrinsically has some value, right? So rather than just taking the reward signal R1, what you can do is you can just take the reward signal negative of V of S1. Like you can just deduct the if the agent is here, you take let's say like let's consider about a rich person. So a rich person opens a company and becomes successful. That reward is not similar to, let's say, a poor person works very hard to open a company and then competes with that rich person's company. So the rich person, by being rich, they had some intrinsic, like the action of them opening a company, it is not much valuable compared to a poor person opening a company. Agreed? Like they had some intrinsic starting point, like the state that they were in had some value. So if you want to compare the efforts of the rich person starting a company and the poor person starting a company, you have to remove the silver spoon, right? This is kind of like you can intuitively think like that. Agreed?
Yeah.
Okay. So this is what is that. So if you are in state S1 and you take A1, you are not only concerned about R1, you are concerned about all the rewards that you are getting after that. Like we have seen, like after a state, then okay, so in each trajectory you will get different rewards. So once you take an action, it can affect all the rewards after it. Okay, so here I have just shown you just one step where you get a reward R1 and then you deduct the intrinsic value. Then this advantage estimator is about all the rewards that come after it. So the action you take A1 not only influences R1, but also R2, R3, R4 until RT. Oops, sorry. Whatever. Something happened. Okay. Yeah, so instead of this, we have the sum of future rewards here. And this gamma is a discount factor. So this is the trade, like this is a hyperparameter which we can tune to see how much weight, like let's say there are, like this is about that marshmallow experiment that we discussed one day, right? Arath, do you remember? I think then there was also there. So some people can give high weight to immediate reward and low weight to distant reward, and some people can choose to give low weight to immediate reward and high weight to future reward, like long-term action, short-term action. So this hyperparameter is something that tunes between that. So these are not really needed, but these are just there. Just know that these things are there. So you have a sum of future rewards that are affected by your action, and then you just remove the intrinsic value of just being in that state from which you took the action. That is called the advantage estimator. Then instead of having this, they found that having this advantage estimator is better than that high variance sum of cumulative rewards. Now we have come until this point. So this now starts to look very similar to the policy gradient estimator that we had. Okay, then now we have come up to this part, and now the expectation is still, we are just carrying down the expectation. The expectation is about the trajectory tau, which is affected by our policy network theta. But inside our formula, we can see that we have removed all the tau dependencies, right? Like we have removed the environment or all, like previously we had R tau. Now we just removed the past from it and then just considering the future ones. So we have we have in a way eliminated the dependency on tau within this part. So we don't have to take the expectation over the entire trajectory. We can just take the expectation over the things that are affecting this function. Here we have states and actions, not the entire trajectory, but the state ST and AT, and this at different times this can change, and then you can just take the expectation over those states and actions which are distributed. Then this distribution is going to be affected by our AT is directly determined by our policy network. Then ST is also kind of like if you do ST, then it goes, like if you do AT at ST, then it goes to ST plus 1. Then that is also a distribution over our policy network. So this is what they are saying. Like instead of like this is just the change of notation, which is being done here. And then like until this part, like there's the theory brings us until this part. So if you look at this equation, it is what, like we have some sort of function, let's consider it f, and then we have an expectation of some our pi is a distribution. Then we have an expectation over that at each step, time step t, there is a function which is affected by a probability distribution, and then we are just summing over all the t's, 0 to capital T. We are just summing over that. So this is our this is the formula for our gradient of the objective function. So like do you have any questions on this? Like we have done all the derivations to bring until this. So now this starts to look like whatever we had in the gradient estimator, like the usual gradient estimator that we had. So here this part is a little bit different from what we have. This part is the same. This part is a little bit different. So here they are saying this is the here the expectation indicates the empirical average of a finite batch of samples in algorithm that alternates between sampling and optimization. So the expectation we have here is a theoretical expectation. So until after this, it becomes hand wave. It becomes like that the expectation had over t, that is like empirical like from here what PPO does is that you run the, like we have removed the black boxes and stuff. So now what they're saying, empirically what they're saying is that like you can let the agent interact with the environment, calculate the advantages, and then this log of policy network gradients, and then get a empirical average over them, and then consider that as a proxy to your objective function. So you can say this is an empirical expectation. You let the agent interact with the environment and collect this data, and then they say this is they go from this part like empirical average can be applied. So there may be some theory behind how you go from this to the empirical expectation, but maybe I need to dig deep. But I hope I have given some intuition behind how they are doing empirical gradient estimation in the paper. So this gradient policy gradient theorem is a existing theorem, and this paper starts from here. So this is what is policy gradient, and then this PPO introduces a way to do this. This optimization can be hard, so they give a way to. There was an algorithm called trust region policy optimization. Then it was somewhat hard to do that. So PPO is just a variant of trust region policy optimization, where they introduce some clip function to do empirical optimization effectively. So they start from this point. So so before seeing how they are proposing some proximal function to this, and there is this concept of importance sampling, where we have seen that when we update the theta, the probability of experiencing a trajectory changes, right? So every time we change theta, we need to let the agent interact with the environment again and then collect. So until today, we have seen how you can calculate the gradient of your objective function without knowing about the environment. But between the once you have calculated that gradient, then if you update the networks of the network weight of the policy, then it changes the probability of experiencing trajectories. The TRPO and I think PPO, like in PPO, they propose some formulation where you can still reuse the old data. Like you don't have to collect. You don't need to throw away the data that you collected with the previous theta network. So that is one of the main ideas. So I will present about them in a separate session. But in this session, I wanted to show you what policy gradient estimation is, what is basic idea of reinforcement learning, what is policy gradient, what is policy gradient estimation, and how each term in that is arrived at theoretically. So yeah, until that's all I had for today. And some of the parts, I'm not a reinforcement learning expert, so I'm not exactly clear. So I have given you my understanding. Any questions on this, on what we have covered today?
Yeah, it's a bit theoretically heavy. You'll have to, I'll have to go through it one more time to have more questions. But you gave a very good explanation.
Yeah, it can be hard. It's like a math topic like that.
Yeah, it is.
Thank you, Niruhan, for a really great presentation. It was a wonderful refresher. It's been a while
Yeah.
since I studied RL, so thank you for that. It was really interesting.
Yeah.
Started from the basics.